hope everyone's doing okay today. Um, I noticed that I actually messed up the due date on the test, but thankfully everyone took it when they were supposed to, so that's good. I accidentally set the test due date to next Monday, not this Monday, but I did intend it to be yesterday, and everyone completed it by last night, so that was good. Some of you expressed some difficulty and sent me your work for some problems. And I think, as some of y'all discovered why that was, is that Canvas is not set up to accept more than one file per problem. If you're working on a laptop or something like or a desktop, then what you could do in that scenario is you can create a zip file and just put all the images into a single zip file or compressed file and send that to me, and I can just open it and get the files from there. It's basically a container for the files. But if that's not possible, that's fine, because like what several of y'all did, I think 4 or 5 of you, you just sent me your work, which is fine. I'll still grade it. Don't worry about that. Anyway, probably by next Tuesday I'll get it graded. That's my goal anyway. We'll see how that goes. All right. Now, today we're going to look at chapter 9, which is, you can see the sections here. We have actually 10 sections, so it's quite an undertaking that we're looking at here. So, I think this week we'll just focus on sections 1 and 2, and then we'll move forward from there. But yeah, this will be our third test, and then we'll have a couple of sections that we cover out of chapter 10, but we won't have a formal test on chapter 10. And what I may do is see if I can come up with some kind of extra credit assignment for chapter 10, just for some of y'all who may be wanting some extra credit by that point in the semester. And I'll see what else I can do, because I know some of you expressed an interest in some extra credit, and I know that some of you definitely need some extra credit after the first test. I wouldn't say definitely need, but you're in a precarious situation. But yeah, I'll see what I can do as far as putting in little assignments here and there, just for something extra. Anyway, yeah. So, and at some point, and I still intend to do this, and I haven't done it yet, so I apologize, because I need a good time to do it, and it's just not been working out. But I keep meaning to make a video going over each of the tests, and I haven't done that yet for the first test, and I'll still have to do that for the second test. That way you can see the problems worked out in a little more detail than what I respond on your work in the Canvas quiz. So I will still do that, and I want to do that pretty soon. I don't know when that's going to happen necessarily, but I'll try to get to it. Maybe Friday. We'll see how it goes. Anyhow, today we're going to look at section 9.1, like I said. So, we're starting on chapter 9, which is infinite series, and you can see there's a whole variety of material that we work with here. And like I said, this is the majority of the remaining part of this course. So it'll probably be well into November when we have a test on this material, like almost to the end of November, I would say, like middle to end. So it's a while away before we end up testing on this material because there's just so much of it. I mentioned that I'll just do 1 and 2 this week, and those may not take the full class times, but some of the later ones are shorter, and I can double up on those as far as lecturing goes, and so that'll be a little bit easier in that regard. And yeah, if you do run into any questions as you're going through homework problems, or you're just looking over material from the assignment, if there's something you don't understand, make sure you email me, and I can either give you a typed explanation, or if I need to, I can create a video for you describing it in a little more detail. So, all right. So, section 9.1, as we can see, is on sequences. So we'll start from there. So, the sequence is defined as a function whose domain is the set of positive integers. Sometimes we include 0, but usually with the sequence we start at 1. I should probably go ahead and say positive integers. So when we say positive integers, that means 1, 2, 3, 4, 5, etc. Okay. And the formula for the sequence can be expressed multiple ways. But specifically the ones that we'll see are f of n, a sub n, and sometimes a sub n in braces. Okay. And the idea of a sequence is we have a pattern of numbers, basically. For instance, f of n equals, let's say, 2n. Okay. If we plug in n equals 1, the first number in the sequence is 2. Plug in n equals 2, we get 4. Plug in n equals 3, we get 6. N equals 4 would give us 8. And n equals 5 would give us 10. And the pattern would follow from there. And so basically f of n equals 2n is a sequence of even numbers. 2, 4, 6, 8, 10, 12, 14, etc. And so that's what that creates. If we say f of n is 2 to the nth power. For n equals 1, we get 2. N equals 2 gives us 4. 2 to the third power is 8. 2 to the fourth power is 16. 2 to the fifth power is 32, and so on. And if we get f of n equals the sequence n squared, which is just a list of the squares, is 1, 2 squared is 4, 3 squared 9, 4 squared 16, 5 squared 25, and so on. Okay. So those are some examples of sequences. Now, there's different types of sequences that we will look at. If we look at these three sequences, the numbers are growing larger and larger. So these three sequences we would say diverge to infinity. So each of these grow larger without bound. So when we say it grows larger without bound, basically there's no number that they're approaching. The numbers are just getting bigger and bigger, which means the values of the sequence diverge to infinity. Okay. The key word there is diverge, or we can say the sequence is divergent because it's approaching infinity, basically going away from everything else. If it doesn't diverge, instead we would say it converges to a specific value, which a lot of times will be 0 if we have like a fractional sequence. It just depends on what the sequence is doing. And the way that we can test this is by taking the limit of the sequence. So the idea is that the limit as n goes to infinity of f of n, where f of n is our sequence definition, whatever formula defines the sequence, we take the limit and we'll say that's equal to some number L. So if L is finite, the sequence converges to L. And if L is infinity, the sequence diverges to infinity. So whether the sequence converges or diverges is based on this limit. Now, we can normally tell if a sequence is going to keep growing larger and larger just by looking at the data values. It's not always clear necessarily, but we'll generally be able to tell if it's going to infinity. Now, whether it converges or not, that's a different question because that's a little bit more difficult to demonstrate. That's why we like to use the limit to demonstrate that. One of the things that you'll notice throughout the first 6 sections of this chapter is that whether we're looking at sequences here in section 1 or series, which is kind of based on sequences, but we'll talk about that more on Thursday. If we look at series in sections 2 through 6, we're very interested in whether they converge or diverge, and that is something that we'll revisit in most of those sections. So, okay. All right. So if we have, for example, f of n is equal to 1 over n. Okay? The limit as n goes to infinity of 1 over n is basically 1 over infinity, and 1 over infinity goes to 0. Anytime we have one divided, a finite number divided by an infinite number, the result will be 0. So we can say the sequence converges to 0. Okay, so this would be an instance of a convergent sequence, because if we plug in, if n is getting larger and larger, then 1 over n is getting smaller and smaller. Because if we think about 1 over n, if n equals 1, we start with 1. N equals 2 gives us 1/2. N equals 3 is 1/3. N equals 4 is 1/4, and so on. And it's just getting smaller and smaller. Okay? And it does eventually go to 0 as n approaches infinity. Excuse me. So that's our limit of a sequence. All right. Let's see what we have next here. Now, because we're talking about limits, it's possible that we're going to have to go back and use L'Hopital's rule in some scenarios. Let's look at some examples real quick. This is on page 596. Yeah. And we're looking at problem let's look at 34. We're given a sub n equals the third root of n divided by the third root of n plus 1. And we want to determine if this sequence converges or diverges. And if it does converge, we want to state what value it approaches, which is naturally part of the process. So I don't know why they asked us to do that, but it's part of it. So we want to take the limit as n goes to infinity of this function definition, or sequence definition, cube root of n over the cube root of n, and then plus 1. Notice the plus 1 is separate from the cube root. It's not under the root with the n, but completely separate. Although it really wouldn't make a difference in this particular case as far as how we deal with this. It'd make a slight difference, but not a huge one. Okay. Now, the issue is here, when we initially plug in infinity, the cube root of infinity is still infinite. Okay? If we take the cube root of infinity, which is still infinite, and add 1, adding 1 to an infinite number is still infinite. Okay, so we get infinity over infinity. Now, if you recall from our Calculus 1 course, this is what we call an indeterminate form, meaning that the value of infinity over infinity cannot be determined. We don't know if that's going to come out to be a finite value, or it may still be infinite value, just depending on what happens with this. And the way that we use L'Hopital's rule, and I believe we talked about this a little bit before, but we haven't really gone into that much. We'll apply L'Hopital's rule. Okay. And L'Hopital's rule says that if we have an indeterminate form, infinity over infinity, or if we have 0 over 0, if that happens to occur, we can take the derivative of the numerator and the derivative of the denominator separately, and then take the limit from there, and it should still be accurate. It's a very handy theorem, in fact, or rule. So this is n to the 1/3 power. Okay, so we want the derivative of that, which the derivative of n to the 1/3 is 1/3 n to the negative 2/3. So just a power rule derivative, we multiply by the 1/3 in front and subtract 1 from the exponent. Okay. So that's the derivative on top. We have 1/3 n to the negative 2/3 power. On the bottom, the cube root of n, same derivative. And the derivative of 1 is 0. So, by applying L'Hopital's rule, we got rid of the 1 in the denominator. And now, as a result, we have identical terms on top and on bottom. Since these are identical, we can just cancel them out. We can do any kind of simplification we want inside of the limit, as long as it's valid. We wouldn't want to make a mistake. But, we can cancel the 1/3, so we can cancel n raised to the same power, top and bottom. And ultimately, we now have a limit as n approaches infinity. If those all cancel out, then we just have a 1 left inside, and the limit of 1 is 1. So our conclusion in this case is that the series converges to 1. Or sorry, the sequence converges to 1. Let's look at 38. Now for 38, we have a sub n is n minus 2 factorial over n factorial. Now, this factorial comparison or calculation tends to be pretty confusing for College 2 students, at least my students that I've had in the past. Initially, it proved very confusing for a lot of my students, although many of them did figure it out eventually, thankfully. Um, so, the way that we handle this, first of all, if we're, I don't have we talked about factorial before? I don't recall actually. So let's define factorial before we jump into this thing. You know, our factorial operator that's our exclamation point there. It's not that we're really excited about those numbers, it's just that we're using what's called the factorial. So n factorial is the product of all the numbers from 1 up to n. So if we had said 6 factorial, it'll be 1 times 2 times 3 times 4 times 5 times 6. And, you know, multiplying all of those together to get the value. So 1 to n. So this 6 factorial is everything from 1 to 6. So we multiply all those together and we get 720. Okay. That's what our factorial is. Now, what is really confusing here for a lot of students that I've seen before is this n minus 2 factorial. We don't know what n is, so somehow we're looking at a number that's 2 less than our unknown value n. Well, let me put it to you this way. What if we actually know what n is? Like maybe n is equal to 7. If we have n equals 7, then we would say for a7, we get 5 factorial divided by 7 factorial. Okay, so we take a number 2 less than whatever n is here. So if n is 7, 2 less than that is 5. And then n factorial on the bottom, so that's 7 factorial. Okay, well, 5 factorial is all the numbers from 1 to 5 multiplied together. And 7 factorial is all the numbers from 1 to 7 multiplied together. And so what we see end up happening here is that all these numbers are going to cancel out that they have in common. Because if we have 2 divided by 2, that cancels. 3 divided by 3, 4 divided by 4, 5 divided by 5. Those all cancel out to a 1. Technically 1 over 1 cancels, but it's still 1 either way. So we're left with 1 on the numerator over 6 times 7 on the denominator, 1 over 42. And that would be our value for A7. Okay. So when we end up dividing these two factorial expressions, since this is everything from 1 to 5 and this is everything from 1 to 7, what ultimately determines what happens is how much further one goes over the other, or instead of the other. In this case, the top stops at 5 factorial, but the bottom keeps going to 7. That means the extra 6 and 7 that we have on the denominator will not cancel out with anything in the numerator. Top stops at 5, so that's going to cancel out everything 1 to 5 on the bottom as well. If we have 1 through 5 on top, then that'll cancel 1 through 5 at the bottom and leave the 6 and the 7 uncancelled. So we end up with 1 over 42 as a result. Okay. The same thing is going to be true for a sub n. The only differences are n is unknown in this case. So let's turn this page over because I'm running out of room rapidly. So continuing that thought, if we have an equals n minus 2 factorial over n factorial, that means the numerator is everything from 1 all the way up to n minus 2. Okay? Whatever n minus 2 happens to be. Our denominator, though, because n is a higher number than n minus 2, keep that in mind, our denominator is going to keep going. It's going to get n minus 2, and again, we keep incrementing by 1, so we get 1 plus 1 is 2, plus 1 is 3, and finally we get to n minus 2, plus 1 would make n minus 1, and plus 1 would make n as the final term. Okay? And so again, we're basically adding 1 each time. So we do 1 times 2 times 3 times 4. We just keep counting upward. So even though we get to n minus 2, counting upward, the next number after n minus 2 would be n minus 1, and then finally n. Because we keep adding 1 to get to the next number. And so what happens is, all these numbers cancel out, everything up to n minus 2, but then the 1 over n minus 1 times n does not cancel, and so that's our result. So an is equal to 1 over n squared minus n. Okay? And if we take the limit as n goes to infinity now, now probably if we're using the limit, it might be better to leave it in this form where it's multiplied together than this form. Because right now it looks like infinity minus infinity. Infinity minus infinity is actually an unknown or indeterminate value. Okay? But if we express that as n times n minus 1, or vice versa, you get 1 over infinity times infinity. Now, infinity times infinity is definitely infinite. And then 1 divided by an infinite number goes to 0. Okay? So when we look at a ratio of factorial terms such as this one, it does get a little bit tricky, especially when they're generalized as they are here, with the unknown value n inside of it. That really makes it confusing, unfortunately. So that's where we have to be really careful and make sure we're counting the numbers properly as we look at what goes into each of these parts. And if you need to write it multiplied out like I did here, just to see what's going to be left over after we cancel, that's fine. It does take a little bit of practice to where you can get to where you don't need to write everything out, and just you can tell by looking at it what the result is going to be. But eventually you can get to that point. Okay? Let's also look at 44 on page 596. Now 44, we have a sub n equals cosine 2n over 3 to the n. We want to know if it converges or diverges. Now again, we can do that by taking the limit, but here's the problem in this case. If we look at the limit as n goes to infinity of cosine of 2n, if we think about the cosine function and what it looks like, my hand slipped, sorry. A little bit larger period on that part of the function. But you get the idea. What's happening with the cosine function is it constantly oscillates between the values negative 1 and 1. And so we get this wave function that never really settles on any particular value. So we say that the limit does not exist because it's constantly fluctuating between negative 1 and positive 1 as the wave function goes up and down. And that continues indefinitely as we continue to infinity. So it really never gets to one number where it stops at. Okay? So that's kind of problematic when we work with a trig function like cosine or sine specifically. The great news, though, is that we also have this 3 to the n term here. And what that does is it allows us to use what we call the sandwich, not sandwich. I may just be hungry. It's called the squeeze theorem, although my friends in high school call it the sandwich theorem. I think because we had calculus before lunch. And now I'm all confused 20 years later. So, there we are. Long story short. Some books may write it a little bit differently, but usually we see it written as the squeeze theorem. Although it may have also been called the sandwich theorem at time. Anyway. It's probably one of those things that depends on textbook. But the idea is that if we can trap this value between two others, we can figure out exactly what happens. Now, what this is going to be based on is the fact that cosine of 2n is constantly fluctuating between this negative 1 and 1 value. Because here we know the bottom, or the lowest value we hit is negative 1, and the highest value that we hit is positive 1. So we can say negative 1 is less than or equal to cosine of 2n, which is less than or equal to positive 1. Okay? We absolutely have boundaries for the cosine function. Now, what that means here is if we combine these concepts together, we can say that negative 1 over 3 to the n is less than or equal to cosine 2n over 3 to the n is less than or equal to positive 1 over 3 to the n. So essentially we took this inequality, which we know to be true about any cosine or sine function, that it has to be between negative 1 and 1 based on where the wave function exists. We divided each of the three parts here by 3 to the n. So negative 1 over 3 to the n is less than or equal to cosine 2n over 3 to the n is less than or equal to 1 over 3 to the n. The reason we can do that is 3 to the n is always a positive number. Okay? And that's actually part of what needs to be true here, is that we have to divide by a positive number, otherwise it creates some issues. Because we are working with inequalities, there are some repercussions, I guess we could say, for dividing by a negative number, in that it changes the direction of the inequality. Anyway, but 3 raised to a power is at minimum 1 at n equals 0 or larger. So it's guaranteed to be a positive number, basically. Remember, n is only the positive integers when we look at the sequence. So n could be 1, 2, 3, 4, etc. So 3 to the first is 3, 3 to the second is 9, 3 cubed is 27. So this is positive numbers, and they're increasing, continuing to be positive. So we know that we're good there. And so what we can do, and this is what the squeeze theorem tells us, is that we can take the limit of this expression, or we can take the limit of all 3 of these expressions as n goes to infinity. Okay. Let me go to the next sheet. So we can take the limit as n goes to infinity of negative 1 over 3 to the n less than or equal to the limit as n goes to infinity of cosine 2n over 3 to the n is less than or equal to the limit as n goes to infinity of positive 1 over 3 to the n. Okay. So we took the existing formula and just took the limit of each part. So the limit of this one should then be less than or equal to the limit of this one. It should be then less than or equal to the limit of that one. Okay. But here's the issue we ran into. We know that the middle limit, we don't know what it is. So we already talked about how the value of cosine 2n never really settles on one value, so it does not have a limit itself. But let's look at the terms on the outside. Negative 1 over 3 to the n and positive 1 over 3 to the n. If we let n go to infinity, we basically get negative 1. 3 to infinity is still infinite. And we end up with a similar result on the right-hand side, although this time it'll be positive 1 over infinity instead. Okay. Now, any finite number divided by infinity, as we already said, any finite number divided by infinity is 0. So negative 1 divided by infinity goes to 0. Now the same thing is true for positive 1 over infinity. That also goes to 0. So we look at this limit that we have now, and we're basically saying that this limit has got to be some number between 0 and 0. Well, the only number that fits this inequality is if the middle number is 0 also. Okay? The only way that 0 can be less than or equal to this limit and also be less than or equal to 0 is if this middle number is actually 0. Okay? That's the only way that that inequality is true. So essentially, by getting the same number on either side, it traps this number in the middle, or squeezes it, so where it has to be between 0 and 0, which means it can only be 0. And as a result, we'll say it converges to 0. Let's look at what's actually happening with this function. So we have our function once again, cosine of 2n over 3 to the n. So before we look at it visually, let's think about what's happening. Cosine 2n is kind of oscillating back and forth between negative 1 and 1. But as n is growing larger, we're dividing by a larger and larger number on the denominator. Okay? 3 to the n just continues to grow bigger and bigger. And it grows very quickly because it's an exponential function. We could say it gets exponentially large. Or grows exponentially. That's the very definition of it right there. And which means it grows quickly. And so what happens is, if we're taking this number and dividing it by a larger and larger number, then the overall quotient is getting smaller and smaller. Because this number on top is always between negative 1 and 1. But by the time we get to n equals 5, this is what, 243? So we end up with 1 divided by 243, which is already pretty small. And if n goes to 6, then we're up to 729, and it just gets smaller and smaller. Okay, so visually what's happening is we have our cosine wave, but the wave is getting closer and closer to 0. Okay? So we have our cosine wave, but since we've divided by this other function that constantly increases in size, that means the overall fraction is constantly decreasing. So our ultimate value is getting closer and closer to that 0. And it does converge to 0 as a result. Okay? Now it actually does this a lot more quickly than I've shown you here. By the time we get to 2 pi, we're already pretty close to 0. So at n equals pi, for instance, cosine of 2 pi is 1, but 3 to the pi on the denominator is something like 30. So 1 divided by 30 is like 0.3. So we're already a lot closer to 0 by the time we've completed one oscillation of this cosine function, which would be right here. So we actually be a lot closer to 0 there. Anyway, long story short, this thing converges to 0. But I wanted to use this example to demonstrate the squeeze theorem and show graphically exactly what's happening here. Alright. So moving forward from there, let's see. There's a few different types of sequences I would like for us to look at. This will also help us when it comes time to look at section 2, when we look at series. Let's look at an arithmetic sequence. This is a sequence in which the same number is added to go from one number to the next in the sequence. For example, we might have a sequence of numbers. Let's say we start at 2, but we keep adding 5s. Okay. So we have 2, but then we just keep adding 5 from every value there. So 7, 12, 17, 22, 27 and 32. So the common difference is 5, and A1 is equal to 2. Okay, so our series, or sorry, our sequence, I keep saying series by mistake. Our sequence is going to be, what is this? 5n plus 2. No, sorry. 5n minus 1 plus 2. There we go. Because we don't have any 5s in the first number, which is, again, this is n equals 1, n equals 2, n equals 3, etc. So n equals 1, we get 5 times 0, which is 0, plus 2 equals 2. N equals 2, 2 minus 1 is 1, times 5 is 5, plus 2 makes 7. N equals 3, we have 5 times 2 is 10, plus 2 is 12. And that's how we would get all these numbers here. And so we would simplify that out. This is 5n minus 5 plus 2. So we could just make it 5n minus 3. But in arithmetic sequence, what it looks like is basically a linear expression. And the common difference is like the slope, and then the starting number is like the intercept. So it's like mx plus b, except we have n and then other numbers. N is our variable, basically. Okay, so whatever the common difference is gets multiplied by this term, n minus 1, and then we add whatever the starting value is if it's not part of the pattern. Even if it is part of the pattern, we keep we keep A1 right here. Okay, and that's how we can create an arithmetic sequence. Those are pretty straightforward. Most of these, depending on the pattern, arithmetic sequences tend to diverge regardless. Anyway, we also want to look at geometric sequence. This is a sequence in which the same term is multiplied to go from one value to the next. It's actually very similar to arithmetic, except arithmetic is the same numbers added to go from one value to the next. Here, they're being multiplied instead. For instance, we might have a sequence in this case where it's let's see, we'll start at 8, we'll go 4, 2, 1, 1/2, 1/4, 1/8, etc. Okay? So we think about how do we get from each number to the next? Well, each number, 8 to 4, and then 4 to 2, and then 2 to 1, we're just cutting those numbers in half. In fact, we are just multiplying by 1/2 each time. Half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is 1/2, half of 1/2 is 1/4, and half of 1/4 is 1/8. So our common multiple is 1/2. Okay. Now, our sequence that we create is AN equals, we'll do 8 times 1/2 to the n minus 1. Okay. Again, this is A1, this is A1 right here, and this is our common multiple, and then raised to the n minus 1. Notice we did the same thing. Here we took our common difference times n minus 1 and added the 2. Here we take our common multiple, raise it to n minus 1, and then multiply by 8, the first number in the sequence. And notice that, okay, our fifth number here, A5, is 1/2. So if we plug in 5, 5 minus 1 is 4. 1/2 to the fourth power is 1 over 16. And 8 times 1 over 16 is 8 over 16, which is 1/2. Okay. So this is the general pattern that's created with geometric sequence. It's pretty close to the same for a series, although we don't have the minus 1. It's actually a little bit easier in that regard. But that's a different type of sequence where we're, two different types of sequences. One where we always add the same number to get from one to the next, and that includes subtraction. And a geometric sequence where you either multiply or divide by the same number to get from one term to the next. Okay. Now there are other sequences that we might see. Some of them are a little bit harder to predict than others. Just to give you some examples. And our question might be, what are the next two terms in the sequence? Okay. So if we have 3, 6, 11, 18, and 27. The question is, what are the next two terms? Okay. So what we really have to do is figure out what pattern's taking place here. Now, we can consider the two that we already looked at, which is the arithmetic sequence and geometric sequence, where we either keep adding the same number or we keep multiplying the same number. But we notice in this case it really doesn't apply. I mean, here we're adding 3 and then 5, so we're not adding the same number. And if we multiply 3 by 2, we get 6, but then 6 by 2 doesn't give us 11, nor does it give us the rest of the numbers. So it's not an arithmetic or a geometric series. Okay. Let's look at the differences. If we're not sure, what I always like to do is look at how do we get from one to the next. Well, this one adds 3. We add 5. We add 7. And we add 9. Now, even though it's not the same number, it does appear that we have a pattern emerging as far as how we get from one number to the next, which is by adding an increasing odd number each time. So 3, 5, 7, 9, the next number that we would add would be 11 and 13. So if we take 27 plus 11, 38 should be the next number in the series sequence. And if we add 13 to that, then 51 will be the one that follows it. Okay. This does require a good amount of logic and intuition to figure out. Some of these are more difficult than others. But that's kind of the thing that we're going for here, is just trying to discern the pattern that's taking place and use that to predict the next two terms accurately. In fact, what's happening here, and you may not see what's happening here, there's actually an easier explanation for this formula that we get here. And it's not that we're adding an increasing odd number each time. The formula in this case is actually n squared plus 2. I've worked with this enough that when we have an increasing odd number difference, I know that I should be looking for a pattern of squares. But it's not just squares, it's off by a little bit. It'd be a lot more obvious if we saw 1, 4, 9, 16, 25, 36. Okay? It'd be a lot more obvious if we saw the actual squares, but if we take those numbers and add something to it, like a 2, 1 squared plus 2 is 3, 2 squared plus 2 is 6, 3 squared plus 2 is 11, 4 squared plus 2, 18, 5 squared plus 2, 27, and so on. So this is the actual pattern that emerges. And so if we want the sixth term here, n equals 6 and n equals 7, at 6 squared is 36 plus 2 gives us 38. And for 7 squared is 49 plus 2 makes 51. It also fits our pattern. Okay. Let's see. What else do we have? Now 46, this is on page 596 still. They give us the sequence 1, 1/2, 1/6, 1/24, and 1/120. And we want the next two terms. Now, again, it doesn't fit our geometric or arithmetic series because we're not just subtracting the same amount each time and we're not multiplying by the same amount each time. But similar to what we looked at here, where we found a pattern among the numbers that were being added, let's look at how we would get from 1/2 to 1/6, or how we would get from 1/6 to 1/24. Specifically, let's look at the denominators. We go from 2 to 6. We can either think of that as adding 4 or multiplying 3. We go from 6 to 24. We can either think of that as multiplying by 4 or adding 18. And then from 24 to 120 is either multiplying by 5 or adding 96. So it's times 1/2 times 1/3 times 1/4. I think we're on something here. Times 1/5. Yeah. The numerator is still just 1, so we're just multiplying by a 1 on top, but the denominator is being multiplied by an increasing value, 2, 3, 4, 5, as we see. And so we can say, okay, well, the next number, here to here, will be multiplied by 1/6, so that's 1/720. And then the next number would be multiplied by 1/7, so that's 1/5040. It's really just pattern recognition. And this is something I always was pretty good at and enjoyed. They can get pretty difficult though, which is interesting to me, but I do like a bit of a challenge in that regard. But there's actually something different going on here if we want to create a formula. And it's because we can see this increasing product multiplier here. What we're actually looking at in this case is this sequence. 1 over n factorial. That's because 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial is 120. Okay? If we look at the denominators, 1, 2, 6, 24, 120, that exactly fits the numbers that we've been getting. So the denominator is basically 1, and then we multiply by 2 on the bottom, so 1 times 2. And we multiply by 3 on the bottom, 1 times 2 times 3. We multiply by 4 on the bottom, 1 times 2 times 3 times 4. That's the factorial. That's 4 factorial, 3 factorial, 2 factorial, and 1 factorial. And so we can utilize that factorial there and create a formula for this expression. Does anyone have any questions on that? Okay. I think that wraps up section 1. I think we'll go ahead and stop there. So let me give you a few problems to look at for homework on page 596. Let's see. Five and 7. What else? Oh, go ahead and try 17 and 19. That's working with the factorial quotients. That'll be useful. What else can we do? On the divergence and convergence, let's look at 29, 37, and 43. That's a good one. And then also look at '45 and 47. Now these two are like the problems we just worked. Now the book gives you a little bit different instructions. What I would like for you to do there is write the next two terms and try to find a pattern. Okay. So look over those. Probably not too bad, I hope, compared to what we've been working with previously. It will get a little more difficult, though, as we go through this chapter, unfortunately. But we won't be doing as much of the integration or derivatives. It'll be more just working with the sequences and series, at least for the first half or 2/3 of the chapter. So anyway, that's all we have for today. So we'll go ahead and stop there. Y'all have a good rest of the day, and we'll do section 2 on Thursday. Y'all take care. I'll see you then.